So what we have done is we are just using extra trees classifier instead of random forest classifier. And here number of estimators we can specify, meaning how many decision trees to grow, how many maximum leaf node we can have, as in the basically what will be the depth of it in the ideal scenario, 4, right? So 4 depth of each of the decision tree. And here we are saying that number of jobs is -1. What does it mean is that we are saying grow these trees parallelly using multiple processors, right? We are going to grow 195 trees, right? Each should not go beyond 16. And we are saying that number of jobs is this, meaning consume all the CPUs available, right? And we are of course providing a random state, which is basically for ensuring that we get the predictable results. Okay, for this discussion, you generally don't need to do random state unless you are splitting your training and test and you are exploring the data over and over. All right, so and then we are doing usual fit, and then we are doing predict on our model, right? And this is happening on the test, this is happening on the training. Okay, so you can see that the accuracy we got is 99.2%. All right, that's not a bad accuracy at all. It's a good accuracy. Okay, while what was the accuracy earlier in case of random forest? In case of random forest, the accuracy was coming out to be 92, right? Using extra trees, we are able to reach 99.2, right? That's a huge jump. So by the way of increasing more decision trees and by the way of adding more CPUs, right, we are able to get better results, right? So by the way of ensembles, what we can do is we can trade more CPU in favor of our results, right? Most of the times we get really good results with using these ensembling techniques. And that's why almost all of the competitions that have been won earlier were based on ensembles. The next part is the feature importance. Important features are likely to appear at the top. Okay, so we can always figure out which features are important based on which one comes first. The features that have more impact on overall tree are generally found at the top. Okay, and the features which are not much important basically might appear on the leaf sides, right? The decision boundaries, I mean the feature thresholds, right? The threshold, the first one will be the one at the top. So it is possible to get an estimate of a feature's importance by computing the average depth at which it appears across all the trees in the forest. And scikit-learn compute this automatically for every feature after training. And you can always find out which features are important using this. Where did it go? We could just say, all right, so you can see best estimator, feature importances, right? In any model, you can take a look. So you can see that these are the two features. These are the two features, and here it looks like the second feature is more important than the first. Okay, so let me just take a look. Right, so it has two columns, right? First and second. The second one is more important. All right, so you can find out that part using here. So this again, we are running random forest on our iris dataset, and you can see that the sepal length has this much impact, while the petal length and petal width have the highest impact. You can see, so petal length has the highest impact, and the petal width has the second highest, and lowest is sepal width. Okay, meaning this is a better predictor. This is a better predictor. This is little less predictor, and so on. So once we have figured out these parts, right? Sometimes what happens is the machine learning can aid the human learning as well. Machine learning can help the human learning as well. This learning we can utilize in other parts. A question from Deepak is, if we calculate correlation in data analysis step, right? Will the feature importance match with decision trees feature importance? So good question. The correlation that we calculate in the beginning, right, is basically using a very simple very simple way. Okay, it's not, and the other part is that the correlation there is generally based on only one column. Here the correlation that has come up is basically based on combinations. So this one is far more important, far more real than the correlation that we do in the data analysis step. Okay, that one is just very vague heuristics. It should not match. This one should be better than that one. Okay. All right, very good question. So you should keep in mind that if you were able to calculate the correlation in the beginning really well, then we would not need to do the machine learning. All right, so great question. So moving ahead. So we find that petal length is 44% relevant and petal width is 42% and sepal length and sepal width is that. Okay. Similarly, if we do the same thing in case of, we were trying to plot decision boundaries here, and the decision boundaries look really bad. All right, so let's take a look at the feature importances in case of MNIST. All right, so what we're going to do is, let's just go down here and here. So we are here, what we are doing is we are first of all loading the MNIST dataset. MNIST dataset is that digits dataset in which we have to predict the handwritten digits. We loaded that, and we are now training the random classifier on the MNIST data. All right, so we are not splitting and all. Right now, we're just training on entire data without splitting. Okay, why? We just want to see the correlation of various features. Okay, so what we are doing here is that using random classifier fit, we trained it on the data part along with the target, and then we defined a method called plot digit. Plot digit basically takes whatever data you give, an array of values, and what it does is it reshapes it into 28 by 28 array, and then it basically does IM show, meaning it shows the image, and now we can use that in it to represent the data. So what is it that we are trying to do is here is we are saying plot digits, and we are giving the feature importances like this. Okay, so let's just test it out what it means. Okay, so you can see here random classifier feature importance. Let's just also take a look at what it means. Okay, so you can see that this is, so what it has given us is the feature importances, meaning the 0th pixel has no importance at all. The first pixel has no importance at all. Third pixel has no importance at all, and so on. So what it has done is it has plotted the feature importances like digit. Okay, so essentially each pixel here represents how important was that particular feature. Correct? So how many features are there? Features are 28 into 28. Correct? And that feature importance is right, those are the variables here. Feature importance is per feature, and therefore it is going to have the same number of values, and hence when we plot it, it will basically show us, in case it's 0, the color is going to be black. That means the black color in this image means that those pixels had no importance. Now you can see that the pixels around here are not at all important, right? The pixel in the boundary are not at all important. All right. So does it make sense to you? Do you think this is correct? That these features are not important, these features are not important, these features are not important, while this particular feature is very important. Okay, and you can see this particular feature is very, very important. This particular feature is meaning the value of pixels here is representing the importance of actual pixels in each image based on the training on the random forest. Which means that if we basically cut this much out from all of this, the boundaries out, even then we'll be able to distinguish the results. Okay? Or from the MNIST dataset, if MNIST dataset, we just cut this small piece and then do the prediction based on that, even then we'll get the good results. Okay, so we have put the legend here on this side, important, not important, and so on, right? Great. So the other idea after bagging and pasting is called boosting, right? Some of you said in the beginning that we could chain the classifiers together so that one after another and so on, right? Okay. So question before moving forward, there's a question from Deepak. Question is, so should we do feature importance and then use dataset with those important features in prediction? So should we do feature importance and then use dataset with those important features in prediction? That's right. If you really need, let's say, why do we need feature importances? Imagine that you are running, you can't really load so much of data, so you need to just take care of only few pixels, few data. So if you take a look at this, even if we let go of, say, close to 50% of the pixels, still we'll be okay. So suddenly when we reduce those many columns, our data size, the memory consumption comes down drastically, right? So feature importances could be used for many things. The first use of feature importance is basically presenting your report to the team that, hey, this is what is my finding. Looks like these are the things that are very important when we are deciding on something, right? So that we also gain some knowledge about what's going on. Second use of feature importance is using feature importance, we can let go of lots of features in our data set. It's very huge tendency that when we talk about predictions, we end up picking so many columns in the beginning, and then we realize at the end that there are so many columns which are not really useful, and therefore we can let go of them in the beginning itself to improve our production pipeline. All right. A question from Manoj is that in case we studied importance features, in case we studied, important features are automatically being considered while fitting and predicting. Is that right? That's right. So no. So right now what we did was when we were doing the random forest, right? When we were training random forest, so it was not ignoring the unimportant features, right? The iterations, the logic, the feature search, the threshold search, all of that, it was trying to do for all the features. Even the features were not important. after all of that work, it figured out that, okay, these are the features which are important and these are the features which are not important, because some of the features, no matter what we chose their threshold, we never got any difference in the left and right labels, right? The number of instances on left, number of right on the right. We never got the lower impurity, right? Which means that those features were not really useful. So during the training so far, we did not let go of, or none of these algorithms actually ignored those features during the work, though they figured out, these algorithms figured out that these are the features which are unimportant at the end of the entire work. Correct. We don't need to really tell which features are important, just that it's a optimization step. Yes, finally it comes up with the right model. Yes. Okay. So yes, we haven't done much of ignoring features, but people used to, when they did all the classical engineering, they did the feature engineering, meaning coming up with new features by combining the existing features and so on, right? And that required a little bit of insight into the data and insight into the columns and so on. And so yes, but we hardly ever ignore the features. We learn how to do the dimensionality reduction very soon, and even before applying the predictions, we can drop many columns. Okay, all right. So point from Deepak is that, but time taken will be more for training with more features every time. Correct. That's right. Thank you, Manoj. Thank you, Deepak. Was I able to answer your question, Manoj? All right, great question. So moving ahead, so all right. So earlier when I was asking that if we have many classifiers, we could chain them together. That was your answer, that we could chain them together instead of doing parallel. So right now, whatever we did, it was like doing the parallel. At one end, we are running the model. At one end, we are running. Okay, so let me go back and start from where I was saying. So so far we did parallel in the sense that we trained every algorithm parallelly, right? And we, in the beginning, you suggested that we could also do sequentially, and that sequence is called boosting. It was called hypothesis. Boosting refers to any ensemble method that can combine several weak learners into a strong learner. The general idea of most boosting methods is to train predictors sequentially, each trying to correct its predecessors. Okay, so there are many boosting algorithms available, and the most popular ones are gradient boosting and ADA boosting. Okay, ADA boost and gradient boost. Basically, whatever the previous one did, it tries to improve upon that. Okay, essentially the chaining part. Now, one way for a new predictor to correct its predecessors is to pay a bit more attention to the training instances that the predecessors underfitted. Also, please note that most of the ADA boost and the gradient boost has been mostly replaced with the deep learning, because these methods were essentially very similar to what we do in deep learning, and and basically gave a lot more, they helped a lot more in coming up with those ideas. Now, okay, so basically, in case, let's say there is one set of predictor, right, who did some predictions and is not doing great on few things, correct? We could come up with new predictor which could basically augment it, improve it. So this results in new set of predictors focusing more and more on hard cases, and this technique is used by AdaBoost. And let me just go ahead. All right, let's take an example. Okay, so imagine that we have first base classifier such as a decision tree, which is trained and is used to make the predictions on the training set. The relative weight, and basically after the decision tree has done, we will keep the relative weight of misclassified training instances is then increased. Basically, we will keep on increasing the misclassified instances, right? The relative weight of misclassified training. I'll just explain to you in more details. So we will first train the base classifier, and whenever the base classifier is making mistakes, we increase those mis weights, okay? And then the second classifier is trained using the updated weights, and again it makes predictions on the training set, where the weights are updated and so on. Okay, so what's happening is that, let's say we took a decision tree, we trained it, and then we started making predictions. We started noting down where all it's making the mistakes. Those instances, basically we mark them, we increase their importance, we increase the relative weights of those misclassified ones, and then the second classifier is basically trained on the misclassified ones of the previous tab. Okay, relative weights as in the ones that have been classified well, we just decrease their weights and so on. So essentially what we are doing is we are picking up on the mistakes of the previous one, okay, and trying to improve from there. Whatever mistakes the first one is doing, the second one is focusing on those parts. Okay, so basically this is, okay, so this is our first base classifier, right? So it's like this, we are going like this, okay, and this was our original data, right? We trained the base classifier and we did the prediction on it, and then whatever result came, and we compared this with our original, compared this with actual, that okay, these are the instances which are done well, okay. Now we train the second classifier. Now for second classifier, what the input is the same instances, just that the weights of the instances, meaning we multiply each row without touching the label, we multiply each row with certain value, certain relative value, and we keep it like this. So you can see that for this classifier, the definition of data set is different. Definition of data set is some instances, right? Though the instances which are not visible here, right? Maybe the instances which really worked well here, they will be disappearing from here. And only the instances that are really not working pretty well using the first one, those instances are left out here, right? And then we do the training and then we keep on doing it. So there are 1, 2, 3, 4 level of boosting. Okay. So here basically, so imagine that the first classifier, imagine that you are trying to make moons. Okay. A question from Deepak is, so does training set size reduce at each step? Not really, not really. The reason why I said that some of the data sets keep disappearing is just to give you an idea that what it means by multiplying the weights or updating the weights. Okay. All right. So it might happen that all the weights of, or the full instance weights become zero at some point. Okay, it might happen. So that's equivalent of all right. Now moving ahead. Okay. Now just take a look at this outcome. Okay. So there are 5 consecutive predictors on the moon dataset, and each predictor is highly regularized SVM classifier with RVF. So first predictor, this predictor you can see, it did lots of mistakes, right? The blue ones are on this side and so on. There are extra this side and therefore it's making the mistakes here. Then the second one, which is basically boosting the results of the first one, is essentially updating, basically working on the mistakes of this one along with this one. So this one is performing better, and this third one is performing a little better, and fifth one seems to be performing great. Actually, the fourth one is also doing pretty well. This fourth one is also doing pretty well. Okay, so the first classifier gets many instances wrong, and the weights get boosted and so on. Okay, all right. So in case of AdaBoost, same sequence of predictors, except that the learning rate is halved, right? All right. So what's happening here is, so we could do multiple things, right? So here there is an idea called learning rate, right? On what, in what ratio the instance weights need to be updated, in what ratio, right? So what we do is we multiply each of the weights, each of the feature weights by certain value. What should that value be, right? So what should the value be? Should we, right? Well, while we computing the relative weights, we can also multiply by something called a learning rate. Learning rate similar to what we learned in gradient descent, but has no relation with it. So every time the new predictor is working on the mistakes of the previous one, and how much more focus should be given is generally there based on how much mistake are we doing, and there one parameter that comes is how much reinforcement should we do, how much what should be the learning rate, right? So the misclassified instance weights are boosted half as much at every iteration. So if the boosting is right, so boosting is low, then what happens is you can see that this does not improve that fast, while this one improves very fast. Okay. All right. So this sequential training technique has some similarities with gradient descent, except that instead of tweaking a single predictor's parameters to minimize the cost function, add a boost adds predictors to the ensemble and gradually making it better, right? So what we generally do in gradient boosting is we keep on tweaking the weights, whatever it has learned, the weights that we multiply to each of the features and so on. We tweak those weights in case of gradient boosting, gradient descent, and but in case of the ADA boost, it keeps it keeps on adding the predictors to the ensemble and gradually making it better. Okay, so what we do in case of ADA boost is we keep on adding more and more predictors, and the next predictor is working on the previous predictor's mistakes, and that's how we keep on improving it. Okay. All right. So once all predictors are trained, the ensemble makes predictions very much like bagging or pasting, except that predictors have different ways depending on their overall accuracy on the weighted training set. Okay. So once we are done with training at a boost, what it would do is we basically let this make the prediction. Now, since each one is making the improvement, since in the chain of algorithms, each one is making slight improvements to the previous one based on what kind of improvements each one is making. Each predictor will have different weights. Okay, each predictors will have different weights. Okay, based on how well they're performing. Question from Manoj is, next predictor can be same as the previous one, or all predictors belong to the different algorithms? In case of AdaBoost, all predictors are the same algorithms, just that the next one is going to restart its training. Okay, so we instantiate the algorithm again and feed it, and again feed it, just like we were growing tree. So when we were basically doing decision tree, essentially we were adding a node, and whatever basically the mistakes were there in the previous one, the next one we're working on that. So if you look at even the decision tree, we were actually doing some way the similar thing, right? We were growing it. And here in AdaBoost, we basically use many decision trees and keep on adding decision trees one at a time. So we added one decision tree, we saw its performance, then we took another decision tree and let the next decision tree work on mostly those instances which are not performing well, and so on and so forth. So we basically keep on adding the decision trees or adding the same model again and again. And generally that has the way MetaBoost is, but theoretically it is very much possible to have multiple predictors or multiple algorithms to do the job. So let me just check. As per my understanding, since AdaBoost grows the values, I'm not sure AdaBoost can use separate algorithms. Let me just see scikit-learn parameters. I'll just say scikit-learn, right? So let's just take a look at the hyperparameters of the AdaBoost. Okay, so we can specify the base estimator, right? We can just give the name. So this is the base estimator from which the boosted tree is built. Then number of estimators, how many you want to do, learning rate, and which algorithm do you want to use. Okay. Okay, so all right. So it gives the feature importances, estimated error, and estimated weights. So it gives the weights to each estimator, and based on that, their values are considered. Okay. All right. So that's about it. So as per my understanding, though boosting can have many algorithms theoretically, but mostly we generally grow the same algorithms. It's easier to grow the same rather than having different ones. So yes, base estimators could be anything. Base estimator could be decision tree, base estimator could be something else. Okay? The base estimator could be SVM, base estimator could be anything. Anything, right? So one thing I want to just, all right. Good questions, good questions. Question from Deepak is, how training data set is modified in terms of size and weights? How training data set is modified in terms of size and weights? We basically do not reduce the size of the training data set in the chain. All we do is we multiply each instance whose weight was not considered. Okay, all the instances where there were errors earlier, those instances we amplify by multiplying with certain multiplier. Okay, or whatever, how much ever mistake each one is doing, we just multiply some ratio of that mistake. Okay. Do we tweak number of classifiers based on the results? Yes, yes. So I'll show you in, where did it go? Okay, let me just take a look. So dynamically, in case of AdaBoost, we basically let them, right? So this is optional. You can see the number of estimators is optional. We let it go. By default, it keeps on going till 50. Okay. And then, all right. So you can see that in case it is perfectly fit, the learning procedure is stopped early. Okay. So based on whether it's learning is going up or down, it basically goes up to 50, but can stop earlier. All right. So there's a little bit of dynamism there, as in terms of stopping. Okay. So it grows the AdaBoost grows the trees. It will keep on adding new estimator only when it's not getting the perfect results. Okay. Question from Deepak is, also, do we do regularization in case of AdaBoost? Do we do regularization in case of AdaBoost? Yes, by the way of specifying all the arguments to whatever base estimator we are passing. We could regularize the AdaBoost by the way of tweaking the base estimator, whatever we are passing, and then by the way of tweaking the learning rate, and so on. All right. Yes, the regularization or hyperparameter tuning we do almost in every case. So AdaBoost can take all the arguments that you were giving to your base estimator. How? Just by the way you were defining the base estimator, you could just change that and then pass the base estimator to add a boost, and it'll take it from there. Our question is, number of estimator can be a hyperparameter? Yes. Number of estimators, if you want to stop earlier then it stops automatically. If you want to stop before that, you can specify how many number of estimators you want to create. Okay, so basically if you specify this, if you mark it less than 50, let's say you're marking it say 10, it'll stop earlier than it should. Okay, and so on. Let's say you can control number of estimators, learning rate. These are essentially two hyperparameters, while all the hyperparameters of base estimator remain as such. Okay, great. Yes, that's right. The results were going bad beyond the fourth step. Therefore, you can stop early. Okay, good point. All right. Now, the downsides of AdaBoost is that it's a sequential learning technique. It cannot be parallelized or only partially, since each predictor can only be trained after the previous predictor has been trained and evaluated. So it's a little difficult to do the AdaBoost parallelly, because for the next one, we need to wait for the previous step to finish, and hence we can't make it parallel. So the boosting technique is not as scalable as bagging or pasting is, right? In case of bagging and pasting, once we have created the samples, we can actually do the parallel work, parallel training, right? All right, just a little bit brief. Don't get intimidated by the the mathematics of it. It's not actually, we do these kind of things very easily, right? Okay, just that the maths look a little intimidating. It's a pretty simple thing. So each instance weight, so what we do is, initially there is a weight of each instance, okay, and what we do is we basically multiply each instance's value. We keep something called the weight of each instance. Okay, so each instance's weight is 1 by n initially, meaning all the instances are equal from the perspective of the algorithm, right? Each instance weight is initially set to 1 by m. The first predictor is trained and its weighted error, we compute its weighted error. Okay, and how do we compute? So what we do is, how many, okay, out of those instances for which the outcome is not matching with actual, for those instances, the weight goes down. Okay, those weights go down. So what we did was, we had like 10 instances, right? Okay, so we had like, say, some instances, say this is my first instance, this is second, this is third, this is fourth. Initially, everybody's weight is 0.25. Okay, everybody is given a weight of 0.25, correct? Because there are 4 instances. Now let's say this one did a good prediction, this one did a wrong prediction, this one did a good prediction, this one did a wrong prediction. Okay, so what we'll do is, these weights now will become how much? Okay, so what we are doing is, we are basically Now, this is, we define the probability of, for an instance selection. So we basically come up with this formula that is predictor's weight, okay? And just describe, so what it means. So basically, we give them weightages. Now, these weights get recomputed, okay? So I'll just say, all right. So let's say at every step, this is being computed at every step, okay? So when the prediction in case of ith instance, okay, is not equal, what we do is we recalculate this. So what was the total weights? What were the total weights? The total weights were 1, right? And here the RJ is being computed for at each step. So this how much is RJ here? The R is basically 0.75. Okay, this is what we calculated, because we did not include this, because this is where the predictions were not, this is where predictions were equal. So actually, no, it was RJ is the point where predictions are not equal, right? Predictions are not equal only in this case, while in rest of the cases, the predictions are correct. So this one is correct, this one is correct. Let's say this said male, this said female, and actual was also, the actual was male in this case, and so on. So we got one mistake, and therefore we got 0.25, because we are saying why the prediction is not equal to the actual. In that case, you sum up the weights, right? So first of all, we define the probability for an instance selection. This is that probability, okay? Now, okay, so what we do in this case is, all right, so what's happening is we got the, all right. Okay, so this is the weighted error, and then the predictor's weight alpha is then computed using this, okay? So it essentially means okay, so if this will be perfect when, this will be 0 when RJ is 0.5, if RJ is less than 0.5, let's say 0.1, it will be bigger. So when RJ is smaller, the alpha J goes, okay. All right, let me just tell you. So now the predictor's weight is then computed. So we got the predictor's weight, the alpha from here. Okay. So this is the weight of each one. So essentially what we are computing is how many instances were incorrectly classified. And based on that, we are marking something called that this predictor was how good. Okay, so basically predictor's value is being defined like this. The more accurate the predictor is, the higher its weight will be. If it's just guessing randomly, then the weight will be 0, because the RJ will be, say, around 0.5, right? RJ will be around 0.5, and RJ will be 0.5 if it's just doing randomly, and therefore 0.5 divided by 0.5, because if it was doing randomly, so in 50% cases it will be right, and 50% cases it would be wrong, okay, if the labels are well balanced. And in that case what will happen is R will be 0.5, right? R represents number of times it went bad. So that will be 0.5. And then we basically get 0. So if a predictor is making mistakes, that means the alpha is going to be 0. If predictor is not making mistakes, alpha will be bigger value. It'll be a bigger value, and so on, right? So first of all, we calculated R, meaning the ratio of instances which are wrong, and I mean the percentage of you can say the fraction of this is the fraction of instances which were wrongly predicted, and then we calculated the strength of each predictor, and afterwards the next instance weights are updated using this formula, right? Using this formula. So what's happening here is we are coming up with new set of weights, right? New set of weights. Okay, these weights, the same weights that we defined just now, these weights will be redefined, right? Either the weight will remain as such, right? In case prediction was correct, okay, in that case, the weight will remain as such. So this prediction was correct, so it will become 0.25. And how much will this be? Say based on 0.25, let's say 0.75 divided by this. So log 3 is how much? 0.6, right? So this will become close to 0.6. Okay, so e to the power 0.6 actually, and then 0.25 and 0.25, right? So this will become more than 1, right? 2.3 to the power 0.6. So you can see that this weight has increased. The weight has increased. Okay. So what we have done is we have come up with the new set of weights. These are called instance weights that we started with equal number of weights initially. So what's happening is we are going to, okay. So what's happening is here again, we'll normalize them. So what's happening is while on one hand, we are feeding these instances to the algorithm, we are noting down we basically giving the credits or scoring each of the predictors, right? All right. So finally, a new predictor is trained using the updated weights, and the whole process is repeated. A new predictor's weight is computed, instance weights are updated, and then another predictor is trained, and so on. The algorithm stops when the desired number of predictors is reached or when a perfect predictor is found. Okay, perfect predictor as in the one which does not make mistakes, meaning this mistake is not happening in that case. Yes, the perfect predictor would most likely be will be overfitting because we are testing it on the same data. All right. All right. So did it make sense? So initially we give each instance a weight of 1 by m. We just set that to 1 by m. And then we train a predictor. We predict how many instances were wrong or right. And based on that, we compute the strength of each predictor, right? Each stage we compute how good was the predictor. And okay, and afterwards, we basically update the instance weights. Okay, so the instances which were misclassified are boosted, right? And After updating the weights, we are creating a new predictor, a new algorithm, and we are training that. Okay, and the whole process is repeated. All right. So these are the new weights. So what we are doing is whatever we were the old weights, we are here. This is how we are updating the weight. So what we were doing, if the prediction was exactly like the previous, if the prediction was exactly like correct, it was correct. Therefore, we are copying 0.25 to the outcome. And then if it is not correct, we're copying, we're not copying as such. Instead, we are doing this. We are multiplying this 0.25 with e to the power alpha, right? So, and then we are doing the same thing here and here. So we are updating these instance weights as we are proceeding, okay? And then we are training a new predictor and so on, and the whole process is being repeated. All right? So we basically keep doing that, and once everything is done, okay? Okay, so once everything is done, what you have to do is you ask, once everything is done, that means that we got the predictors, we got a sequence of predictors who can do predictions really well. And okay, so so once we got a chain of predictors after the training is finished, so the ADA boost for doing the predictions, what it does is it simply computes the predictions of all the predictors and then weighs them using the predictor weight alpha, right? Since it has come up with these predictors which has got some predictor weights, and so based on the errors each one was doing, we came up with the predictor weights, and we ask all the predictors, all the stages that we have come up with here. Okay, where is the diagram? Okay, so at every stage there'll be one predictor here, there'll be another one, and so on and so forth. What AdaBoost does is it asks all the predictors for their opinions. Okay, and what it does then is that it gives them weightages. Okay, and the one which has got the highest weightage is the one which is going to be considered. Okay, the predicted class is the one that receives the majority of the weighted votes. Okay, again, here we got many predictors, we got like 10 algorithms, right? Imagine for a moment that we got 10 algorithms. Each of them is capable of doing predictions. Some of them are more capable than the other, that we know based on the alpha, right? So we got the predictors who can do the predictions, and we got their some of them are really good at even predicting the outlier, right? So even predicting the outliers and so on. The one that is able to predict the outliers, we give that better alpha, we give that more score. And once we are done with training, when we are predicting, we utilize this value given to all the predictors, right? So there are some more important, some are less important, and some are more important predictors, or some algorithms or models, whatever you want to call them. And then once everything is done, we basically, based on their priorities, the weighted mean, we compute the overall probability, overall probability. Okay. So what we do is we first find out which one is coming out to be the better. Like there are 10 predictors, each one is doing some prediction. We give each one is giving some probabilities, and then we multiply each of the probability with their corresponding alphas, and the one which is performing really great will get more weight, their opinion will be mattering more, and hence the outcome will be the soft votes of the overall. Okay. All right. Question from Deepak is that what is K here? K is basically what we are doing, that we are finding that yj x equals K. So essentially what we are doing is we are taking the opinions of all. Okay. And here that formula doesn't show it clearly. So, okay, let me just put forth probably in this diagram. So here what we're saying is we got, say, 3 predictors, okay, with some alphas. The first one is having, let's say, how much? Say a value of 1. Okay, I think the alpha is going to be somewhere between less than 1, right? So if alpha is okay, r is going to be less than 0, between 0 and 1. This is going to be between 0 and 1, right? So it's going to be between 0 and 1, and this is also going to be between 0 and 1. Numerator is going to be between 0 and 1, right? And numerator is going to be between 0 and 1, and denominator also is going to be between 0 and 1. Okay. Okay. And log of that is going to be this. Okay. So it could be anything, right? It doesn't necessarily be, alpha is not going to be necessarily between 0 and 1. Let's say there are first predictor, let's say these 1, 2, 3, these are first predictors, and this is our alpha. Let's say it's called, the first one is doing some mistake, second one is not doing some mistake, third one is, let's say, again, let me just make it 15. Okay, so we asked when we did predict, we ask each of their opinions. This one said that 0.1 is our main class, right? This one says 0.2. This one says, say, 0.15. Okay, so what we do is, I think there is a soft voting here, as per my understanding. You just multiply this with, here we say that, okay, we multiply the predictor's weight, so it could become 0.5, and this becomes, okay, and this becomes probably 2, this becomes 2.25, right? And then okay, so then we sum up their, okay, so similarly we compute the other class also, say 0.9, 0.8, and 0.85, right? There will be the negative and positive ones. This will be 0.45, or is it going to be 4.5? This is going to be 4.5. This is going to be the 8, and this is going to be how much? This is going to be 12.25, right? So we sum up, as per my understanding, we sum up their probabilities all across, and we pick up the one which is giving the maximum value. Okay, so no, we pick up the, right? So either we could do multiple things. We could just pick up the, let's say, here, okay, and so on. So essentially we could sum up these votes from everyone and then figure out which one is important. The most important part in this to understand is that if the under the hood, whatever class we are using, under the hood, it is going to give us the probabilities. We multiply that with alpha and we get these results. Okay, so and then we pick up the class which is getting the maximum majority. K here probably represents class, okay, or K represents the predictors. Yeah, K represents the class. So overall the class which is getting the maximum soft vote, we pick up that one. All right. Now you might be wondering that why I have taken alpha j here and here this probability. So there could be two kinds of predictions in which we are getting either yes or no, okay, or we are getting the exact probabilities. So here in this formula, what's happening is we are basically assuming that the underlying classifier, whichever we are using, is not giving us probabilities, and therefore we are only talking about 0 and 1. So we pick up the opinion of the one. If we imagine that this was not decimal number, it was either 0 or 1. In that case, of course, only the alpha would matter, and that's how it is. All right. So basically, in case underlying algorithm is not giving us probability, then we will have to basically go with the opinion of the one which is having the maximum alpha, right? The alpha algorithm, right? And otherwise, if it is giving the probability, we multiply the probabilities of each underlying algorithm with alpha, because alpha represents whose opinion matters most. And then we basically do compute the sum of all the classes all across and pick the class which is having the maximum value, right? So if let's say algorithm is lower alpha, says that hey, says that it's a class A, and the one with higher alpha says it's a class B. In that case, the class B's opinion would matter more. All right. So the edge cases are basically because in case of the non-edge cases where everybody is clear about certain instances, in those cases all the predictors will have the same opinions. On the on the cases which are nearer to the boundary, in those cases the importance of some predictors will be more visible, okay? Otherwise they will all have the same answer. So let me just take another example. I'll just draw the example here. So imagine that we had two predictors, right? This is predictor 1 and this is predictor 2. We computed their alphas over the period of training, right? And we realized their corresponding values. Let's say this one's value is 2, then this one's value is 3. Okay, correct? Now let's say that we give an instance, I instance, and P1 says 0 and P2 says 1, right? So here basically it's saying that given this photo, it's a male, other one is saying it's a female, right? Now we have to pick up whose opinion. So this one's opinion would matter more. Okay, so that's what is showing here. So we basically take up the opinion of each one. So this one is 2, this one is 3 here in this case, right? and we say that which one is having the maximum alpha from 1 to n, where the jth prediction is same as the outcome, where the okay, so we basically finding the maximum of it. Okay, so max of 2, 3. Okay, so the max of 2, 3 is this one, and argmax means it's this one. So argmax means the one that is giving you the max results. Okay, again, those who are not clear about argmax, I'll just show you what it means. Okay, generally the argmax is a bit of confusion. np.argmax. Okay, okay, so you can see what will be the argmax. Argmax is 4, meaning the fourth value is max. All right, that's what we are also saying. Over all the predictors, whichever is giving the max value, we're going to pick that. No, actually, the prediction. Okay, so as we are saying that whichever algorithm gave better results, we pick that value. Okay, so it is 1. All right. So right, that's about it. So essentially, again, what we are doing over here, that we are training more and more algorithms over the same data after updating the weights. All right. I don't see this weight being used in the training. Okay. Okay. All right. So all we are doing is we are basically updating these alphas. Alpha, in the calculation of alpha only, we are utilizing the weights. I don't see that the actual weights of instances being touched anywhere. These are only weights used for calculating the alpha. All right. So yes. So at the end of the entire process, we would know that which predictor is great, and we will value that predictor's opinion more. That's all about AdaBoost. All right. So scikit-learn actually uses the multi-class version of AdaBoost called SAM16, stage-wise additive modeling using a multi-class exponential loss function, where there are 2 classes. SAM is equivalent to AdaBoost. Okay, so right, so AdaBoost essentially, it was basically 2 classes earlier, and then just by changing the underlying algorithm, AdaBoost can work with multi-class. Though in case of scikit-learn, it doesn't matter. In case of scikit-learn, it figures out based on the number of classes that whether to call SAM or whether to call the usual default one. Okay. Moreover, if predictors can estimate class probabilities, if they have predict prob a method, okay, scikit-learn can use the variant of SAM called SAM-R. R stands for real, which relies on class probabilities rather than predictions and generally performs better. Okay, so basically this formula changes when the values become real, right? When the underlying algorithm is giving you the probability instead of only picking up the one picking up the opinion of the one which is having the best alpha. Instead of that, we multiply with the actual predicted probability in case the underlying algorithm could give us the probabilities, right? All right. Thank you, everyone. I look forward to see you.